Yesterday, I brought up this function, x to the x, where we have a variable as a base and a variable as exponents. We have rules for dealing with derivatives, at least we have derivatives and integrals for a variable raised to a constant and for a constant raised to a variable, but we don't have anything for a variable raised to a variable. The reason for this is that it's kind of a niche problem, but it has to do with some of the stuff that we did last week as we fill in some more details for Calc 1 before we finish up for the semester. So we're looking at this function x to the x, where we have a variable raised to a variable. And we want to think about the usual kinds of questions that we ask when we're in calculus. What's the equation of the line tangent to this curve at a couple of different points? Find the local maximum and local minimum. These two questions are questions about derivative. So these are derivative type questions. The second question, or third question, I guess, what's going on with f of x equals x to the x when x is negative? This is just more of a describe stuff type of question. That's one of the other things that we do in math. We spend a lot of time describing stuff. And then the third question, like none of these are actual question. Only one of these is an actual question. Semantics. The third part, find the integral, definite integral from 0 to 2 of x to the x dx. This is obviously a definite integral question. More interestingly, I wrote this kind of without thinking about it too much because I just wanted to say, oh, I'm going to have derivative questions that aren't just find the derivative. Going to have some questions about this function in general. And then I'll have a definite integral question. And I just kind of like casually wrote the integral from 0 to x, 0 to 2 of x to the x dx. So that's just an integral stuff. But it actually became more interesting than that because I wasn't paying attention. Because this is the definite integral from 0 to 2 of x to the x. Now, the problem here is that 0 to the 0 is not defined. We don't have a value for 0 to the 0. So all of a sudden, even though I just wrote this because I wasn't paying attention, rather than change that from like 1 to 2, we have this, what is 0 to the 0? What's going on with this 0 to the 0 business? So that's kind of interesting. So without even thinking about it, I threw in a question, which is more of a Calc 2 question, so I don't really have to address it today. This is an improper integral. When you're, one of the things that we need for our fundamental theorem of calculus is we say let f be continuous on the interval, the closed interval from a to b. And here we have a function that is not continuous on the interval over which I want to integrate. That makes what we call an improper integral. Another way to have an improper integral would be to integrate from, say, 1 to infinity. So there are a few ways that we can have an improper integral. At some point, the function is discontinuous in kind of a radical way, like this function goes to infinity. So I kind of accidentally did a kind of a more advanced problem. But that's fine. That's fine. Let's not worry about it. So the point that I wanted to make here is that we don't have rules for the derivative of x to the x. I don't have an expression for an x to the x. I can't use my nx to the n minus 1 because that's when we have a variable raised to a constant. I also can't use my a to the x because that's when we have a constant raised to a variable. I also can't do kind of the stuff that we like to do is like, well, what if things aren't variable? Because both parts, the base and the exponent, are both variables, and they're the same variable. So I can't just hold one of the x is variable constant while the other x is variable. That's just not how things work. So the things that we can think about, the ways that we could go about this problem is to remember what these things represent. This is why we're coming back to that first day of class. We talked about the two big questions in calculus. When we have derivative stuff, we like to think of find the derivative, plug in the shit that you need. But in this case, we don't have that find the derivative part. In the definite integral thing, we'd say, well, find the antiderivative, plug in the endpoints. That doesn't work as well because we don't have an antiderivative. So we have to think about what these things represent. Derivative stuff, like we've been talking about last couple of days, this is slope stuff. Integral stuff, definite integral stuff anyway. That's area. So even though we don't have a way to find derivative and antiderivative, we can still make these calculations. We can approximate the calculations. So even though we don't have mechanics for finding derivative, antiderivative, of x to the x, we can approximate what we're looking for. We can approximate what we want by remembering what the derivative is supposed to tell us. We can approximate stuff by remembering what the integral is supposed to tell us. Then, at least in the derivative, some of you may have noticed already, we actually can find that one, we just haven't yet. So just going back to our first principles, if we think about what the derivative is supposed to represent, we can approximate f prime, let's say approximate f prime at 2 by choosing a point a little bit away from 2. So like, let's say 2.1 raised to the 2.1 minus 2 to the 2 over 2.1 minus 2. We can approximate the slope in the same way that we approximated at the beginning of the class. We want to find the slope. It's at 1 point. Can't do slope with 1 point. Pick a point nearby. If that's not sufficient, or if we just want something better, then we move the points closer. Pick something closer. If we want something better, then we just move stuff closer. And because this is calculus, if we want the exact value, we just do this forever. We make those points infinitely close together. Then we get one of those situations where it's actually useful to have an old style graphing calculator. As usual, bad for graphing, great for a lot of other things. We do have to recognize that our function looks like x to the x, so we're going to have to put in this 2.01 a bunch of times, but we're going to divide by 2.1 minus 2. I'm just going to simplify that. See what we get here. 7.496. That point is really far away, so I'm going to insert, I'm going to move closer by a factor of 10. Now we look at how much this changed from 7.5 to 6.8. This was a big change, so maybe we should go closer because 2.1 was clearly not very good. So we just keep going. This was the original thing that we did when we first introduced these two questions. Any questions? Comments? Slide them on. As you watch me clumsily put these in one at a time, might be thinking there's probably a better way to do this, and I'm sure that there is, but this one shows us exactly what we're trying to calculate. This reminds us that when we're looking for a derivative, we're looking for a slope. But at the very least, we've got this, it went from 7.5, that wasn't very good, down to 6.8. We don't know how good that was, but now we moved by closer by a factor of 10 again, and we're at 6.779, and then moving by closer by a factor of 10 yet again has only dropped up to 6.773. So we feel like we're zeroing in on something. I'm going to do one more, so I can't stop. Now, if we were this one, we got another 6.77 rounded, it would be 6.773. If I was looking for something to 4 significant figures, I think we're there. This is how close we needed to be. We didn't have to take that many steps. And we're not even that close, 2.00001. Any questions? So we're able to do these things without actually finding the derivative. We can get at what we want without actually finding the derivative. If we're just going to be punching stuff into the calculator, we can also grab, for the second one, we could just grab an actual graph of the function, and Desmos will say, here's where the minimum is. And that'll be to 3 decimal places. In the category of finding an area, we can approximate the area by just evaluating the function at a bunch of places. So we can start off with, we can start building a table of values of x and x to the x. Well, this one is problematic. In the middle, we got 1, 1. But if we start just putting in more values, then we get a better approximation. Here we can calculate the area with n equals 4. Now, notice if we ask for 0 to the 0, when we ask for 0 to the 0, that's the calculator is like, oh, this is unacceptable. We can't do 0 to the 0. We get an error. We can't use the word error in our calculations. So we're like, oh man, bummer. But we remember that we're approximating. So, all right, calculator, what if we just did something close to 0? Maybe we should just try something close to 0. Any questions? This is information that we can also grab from looking at the graph. That would be a fast way to find values on our function, especially on Desmos. We can just drag our cursor along the graph. But once we have a table of values, so this 0.001 to 001. Actually, if we think about it this way, we could kind of examine. Maybe we want to examine what we can use for 0, for f of 0. We can't, there's not actually a value there, but maybe we can kind of like fudge something because we're approximating, right? So it looks like we should get 1. Then when we look at the graph on Desmos, we can see, yeah, 1 makes sense. When we plug in 0, we don't get a value, but it looks like we're headed towards 1, at least from the right side of it. Yeah, and the 0.5 being at 0.7071, that's the square root 2, half the square root of 2. That explains that shows us that it dropped down before going back up again. So there's some things that we would want to make sure that we capture if we're making an approximation. So it looks like as this, we can't plug in 0, but as this heads towards 0, it looks like our value is headed towards 1. And the graph would confirm that. If we try the negatives, this is going to give us some good false information. That's kind of awesome. Using too much 10 is working. So in this case, when we look at negative values, our approximations close to 0 are giving us close to -1. So clearly the limit, the two-sided limit as x goes to 0 doesn't exist. And we saw that in the graph. We saw a graph on the positive side of X, and then we saw like very sporadic graph on the negative part of X, when X is negative. So the limit doesn't exist, but for the problem that we're trying to do, if we just want to calculate the area from 0 to 2, we kind of don't care what's going on when X is negative. The problem is set up so that we only care about when X is positive. Any questions? How's everybody okay? I'm not even sure if I don't know if my calculator will do. I didn't even try this. So apparently our calculator is okay with the limit being 0. But now I'm curious. Okay, there we go. Any questions? If we remember what these things represent, even if we don't have a method for finding an antiderivative, even if we don't have a method for finding the derivative, we have ways of dealing with these questions. Derivative, slope, definite integral, area. Those are the things we want to carry moving forward. Any questions? So I did mention that we actually can find the derivative of x to the x. And we have all the tools in place to find the derivative of x to the x. It feels like a niche problem when we actually employ the method. But the overall picture is recognizing what the issue is and recognizing what tools we have at our disposal. The problem here is that I've got a variable raised to another variable. That is a problem. A lot of times exponents can be difficult. Exponents can make our lives difficult, especially when we have a variable raised to a variable. So the problem in the setup, this is what I almost talked about yesterday in class, because I wrote 253. So I'm like, oh, Stokes' theorem. Everybody would have been stoked. Oh, look, vectors again. The issue is I have variable base and variable exponent. That's the issue. First of all, we have to identify what the problem with the problem is, the issue, variable base, and a variable exponent. The operation here is exponents. Variables in both pieces. Don't like it. This issue shows up a lot. So C also. Let's suppose we wanted to solve an equation like 2 to the x equals 3x minus 4. I don't even know if these intersect. The problem here in this equation, it has the same issue. We don't have technique for this equation because there's a variable in a base and there's a variable in an exponent. So this is the kind of equation that we would ask you to solve. Once we taught you that calculators can do things. Once we had said, hey, you know that we're trying to look for where two graphs intersect, and you know it's pretty good at making graphs. And Texas Instruments is like, oh, yeah, you know I'm pretty good at making graphs. I can't do a Texas accent, so don't come at me in the comments, Texas. Especially the problem, don't make fun of, don't mess with Texas because they'll probably shoot you or something. I don't know. I'm surprised that this doesn't come like. This is a Texas Instruments calculator, but it's a California edition because there's nowhere to put the bullets. All right, what are we talking about? Oh, I'm just kidding. They don't have electricity in Texas, so they're not watching this anyway. So what are we talking about? Also, don't get it wrong, California is ridiculous too, so. You can tell they're ridiculous because these are all like made by people, and people are ridiculous. What are we talking about? Oh yeah, Texas is stupid. So we've got x to the x. The issue is that there's a variable base and a variable exponent. Just like we have 2 to the x equals 3x minus 4. The problem with that equation, we don't have a technique for solving that equation exactly, because there's a variable in the base and there's a variable acting as an exponent. Not even in the same term, it's still a problem. So this x to the x concentrates it all in one place. What we do have is stuff that moves exponents out of exponents. If I write the natural log, it doesn't have to be the natural log, it could be log of any base of x to the x. We can write this as x times the natural log of x. Logarithms, properties of logarithms have that the natural log of a power is a constant times the natural log. This isn't doing funky derivative stuff. This is just properties of logarithms. Now, when we look at our expression, there's a natural log. We've introduced that natural log. So that is a concern, but everything's just being multiplied. There's no more variable exponents and variable base. I guess technically there's a logarithm, so that's an exponent, right? But it's in a form that we can work with. The x's are combined through multiplication in this natural log. They're no longer a variable exponent and a variable base. So if we write the equation y equals x to the x, I can rewrite this with natural logs, but we have to do the natural log of both. So what this has allowed us to do is take this problem parts, variable base, variable exponent, and move the variable exponent down into a multiplication. So now there's no longer a variable exponent. On the left side, we can use our implicit differentiation, and then on the right side, we just use the product rule. From here, we can get an expression for dy dx, which is the derivative of y with respect to x, and then we can start plugging stuff in. So on the left side, we're going to use implicit differentiation. The derivative of the natural log of something is 1 over that thing times the derivative of that thing. On the right side, we're going to use the product rule, which says take the derivative of the first times the second plus the first times the derivative of the second. So solving for dy dx, we just multiply both sides by y. And then 1 times natural log of x is just natural log of x. X times 1 over x is just 1. This is an implicit description of our dy dx. It involves y and x, but we have an expression for y. So we could also write this as dy dx is x to the x times the natural log of x plus 1. I know yesterday when I wrote down x to the x, you're like, oh, it's x to the x times the natural log of x plus 1. And I'm like, oh, I didn't tell you. And like, oh, come on, dude. Everybody knows that the derivative of x to the x is x to the x times the natural log of x plus 1. You were all thinking that, right? I'm not going to verify that with the divided type of test. So you just be like, oh, yeah, we were told. Of course. Any questions? Comments? Snyder? Yes. What do you mean if there's a it was 3x to so like 3x to the x. So mechanically we would do the same thing. We would natural log. That would pull the x and leave the 3x in here. So when we take the derivative, we take the derivative of the first times the second. So that 3x would still be there. Yeah, it just kind of hangs out. Now, when we take the derivative of natural log of 3x, it's 1 over 3x times the derivative of the inside, which in this case is 3. Oh, and I need the x because I'm doing a product rule. So derivative of the first times second plus the first times the derivative of the second. The derivative of natural log of stuff is 1 over that stuff times the derivative of that stuff. So the 3's end up canceling out. But the 3 would still show up in this natural log of 3. One of the reasons that 3's cancel out, though that 3 cancels out, since properties of logarithms, if we think about this problem, this here, when we write natural log of 3x, natural log of 3x is the natural log of 3 plus the natural log of x. So properties of logarithms, the natural log of a product is the sum of the natural logs of the factors. This is because they're behaving like exponents. Remember, logarithms are exponents. So when we multiply things with the same base, we add the exponents. Now, if we had expanded the natural log of 3x, the natural log of 3 plus natural log of x, the derivative of the natural log of 3 would be equal to 0. And we just have this extra natural log of 3 times x term. So good news, properties of logarithms allow us a lot of ways to go about to deal with this. Bad news, properties of logarithms are everywhere. Best thing to do is whatever occurs to you at the time that you're doing it. You know what I mean? It's like when you're trying to show your friend how to do something on a computer and you're like, oh, you right click here and then someone else does something different. It's like, well, you don't go right clicking there. What you do is go up to the menu. It's like, well, right click, menu, right click, menu. And meanwhile, the program's like, oh, it doesn't matter. And you're like, oh, no, this is Coke versus Pepsi. This really matters. This is Mac versus PC. This really matters. This is PlayStation versus Xbox. This really, it's all the same thing. I forgot. This is Camry versus Accord. I think it'd be kind of awesome if Toyota and Honda kind of teamed up in their advertising, and instead of trying to compete the RAV4 against the CRV, they just like joined hands and joined together in a commercial. And it was a Toyota / Honda commercial. It's like, oh, RAV4 or CRV, just pick one. They're great. I don't know, all you car enthusiasts be like, oh, but they're so boring. It's like, well, yeah, some people want that in their car. Some people don't want a machine that they could just modify. They just want the Toyota Camry of computers. For those of you at home, I'm holding up my MacBook Pro. It's a Toyota Camry of computers. No, you can't modify it. I just needed to do stuff. You can't play games on it. That's good. That is a feature, not a bug. There's a reason I didn't build a laptop. You think I'm slow at grading now? If I had a fucking gaming machine in my office, I wouldn't even be here today. Because I would have been fired for gaming in my office. Any questions? Comments? Snide Robot. It's awesome. I actually tried to put Baldur's Gate 3 on this computer and it could not. It was like, oh, come on, man. It was running. It did its best. It did its best, but the frame rate was like 60 seconds per frame. Not 60 frames per second. It just like inverted that. 60 seconds per frame. So it was like it was awesome, but kind of unplayable. Any questions? Comments? So this highlights not the importance of this problem. This function is a stupid function, right? Who cares about this function? After this class, you'll never run into this function again. And it won't even be an interesting problem when you do run into this function again. So later on, if a teacher brings up this function, pretend like you've never seen this fucking shit before. Don't be like, all spoiler alert. You just, oh, let's do logarithmic differentiation. Don't do that. Just play the game, right? Read the room. It's like, oh, this professor thinks they're doing something. Let that. I'm going to pretend that I don't know the trick, and we'll see where this goes. Does that make sense? A lot of times you need to think of professors as like, like 4-year-olds. If your 4-year-old comes up with something that they want to show you, you know it's probably going to be dumb, but they're really excited about it. So fucking play along. You know what I mean? I don't know how many of you have to deal with 4-year-olds on a regular basis, but it took me a long time to figure out I should just play along because the kid is having fun. So, any questions? Comments? Snide remarks? All right, that's going to do it for today. That's going to do it for this week. I'll see you all on Monday. Everybody have a good weekend, and thanks for playing.